Aloha and welcome to my talk, A True Virus on macOS. So my name is Patrick Wardle. I am a principal security researcher at Jamf and also the creator of the Mac security website and tool suite, Objective-C. So today we're going to be talking about a rather intriguing piece of Mac malware, which we've named EvilQuest. We're going to start by detailing its infection vector. Then we'll dive into the malware's internals after we've done a brief analysis, a brief triage of it. And then we're going to finally end by talking about its persistence mechanisms and capabilities. First, however, I want to give a shout out to Dinesh for uncovering this malware, as his tweet definitely intrigued me to dig more into the malware and perform a full analysis, which I am now talking about here today. So the first question we had is, how does EvilQuest infect macOS systems? That is, how does it get macOS users to basically infect themselves? So to answer this question, we turn to the noted Mac security researcher Thomas Reed, who noted, as we can see on the slide, that EvilQuest was uncovered and was spreading within pirated applications via popular torrent websites, predominantly on Russian torrent websites. So the pirated applications infected with EvilQuest were a mix of popular commercial software tools. For example, the popular macOS firewall, Little Snitch, as we saw on the last slide. Another example, the popular commercial DJ application called Mixed-in-Key 8. And for the remainder of this talk, we're going to focus on a sample that was found within the Mixed-in-Key 8 package. Now, this package was unsigned, meaning that when the user downloaded it from the torrent site, macOS would put up some prompts and alerts that the users would have to manually click through. But apparently, this was not a deterrent for consumers of pirated software. They're probably not too surprised where these packages are unsigned. So now we know how EvilQuest infects Mac users, right, via these pirated applications that have been Trojanized. Before, though, we can dig into its persistence and capabilities, we need to perform some initial triage. This is going to allow us to determine how to decrypt its encrypted strings and also allow us to both identify and thwart its anti-analysis logic. So notice we're going to be focused on the pirated and infected mixed-in-key application. This was distributed, as we noted, via torrent sites. And in this case, it was distributed as an Apple disk image or a DMG file. So once we download this file, we can mount it via the HDI util command, and we can see it contains a single package named mixedinkey8.pkg. Now, my favorite tool for analyzing PKG or packages is aptly called suspicious package. Using this free tool, we can statically analyze the package contents. For example, we can see what files it contains, what scripts are run. It's a really nice tool for performing static analysis of PKG or package files. So using this suspicious package tool, for example, we can see that there is an application called Mixed-in-Key8, which we can extract, we can export. And if we look at the code signing signature, we can see it's still valid and that it's been signed by the Mixed-in-Key8 developers. So this means this is likely pristine, unless, of course, the hackers had some way to steal or use the developer's actual keys. But in this scenario, I thought this was rather unlikely given the unsophisticated distribution mechanism, right? If you have the ability to distribute developer keys, you're probably not distributing pirated software via torrent sites. More interestingly, though, was a second binary, and this was an unsigned macOS binary called patch. Also, via the suspicious package tool, we can see that the PKG file contains a post-install script. So during the installation of the PKG file, right, when the user's double-clicked on it, the user will be prompted for credentials. After the installer has moved all the files into place, the post-install script will be automatically executed. Again, using the suspicious package tool, you can extract this script. I've shown it on the slides. It's about 8 lines of code. And you can see basically what it's doing is it's moving the unsigned patch binary into a directory called mixed in key, and then renaming the binary to tool room D, which is then launched in the background. So let's take a look at this unsigned patch binary, or as it was renamed, tool room D. Now, one of the first things I do when analyzing a unknown or unrecognized binary is to run the strings command, which, as I'm sure we're all aware, has the ability to extract embedded ASCII strings. Turns out there's a lot of really interesting embedded strings within the malware that the strings utility can extract for us that provide a lot of insight into the malware's likely capabilities. Also, which was kind of most interesting to me, is we can see that the strings command revealed a path which contains the malware author's name for the malware, which is effective idiot, or EI for short. And we'll see in the remainder of the talk, there are various function names or method names within the malware that have this EI name appended to them. Speaking of symbols, we can also run the NM utility, which can extract embedded symbols and APIs that the malware imports to invoke. These APIs are interesting because they, again, can reveal the malware's likely capabilities. But even more insightful are the actual names of the malware's functions or methods, which, again, as we can see on the slide, give us insight into the malware's likely actions, its features, its capabilities. So this is really kind of a good way for us to get a good sense of what the malware likely is going to do, based on just symbol names and the names of the methods or the functions that the malware authors are kind enough to leave in. Now, when I ran the strings command, I noticed that there were definitely large chunks of what appeared to be encrypted strings. If we hop into a disassembler, we can look for cross-references to these strings, and we can see they're all passed to a function named EI_stir. Again, this EI referring to the malware author's name for the malware, effective idiot. Now, as malware authors, obviously we want to decrypt these encrypted strings because a lot of times the more interesting strings, the more sensitive strings, have been encrypted by the malware author in an attempt to, let's say, hinder or slow down analysis. So there's various ways to decrypt such strings. You can understand the encryption algorithm, perhaps write your own Python script to decrypt the strings. I'm a little lazy, right? I want to be meditating at the beach instead of staring at my screen all day. So I figured I would take what I thought is a simpler route. So what I did was I simply created an injectable dynamic library that I could inject into the malware while it was running. This injectable dynamic library would then resolve the address of this EI_stir function, the string decryption routine, and then simply invoke this string routine on all the embedded encrypted strings and then print those out to standard out. So in other words, I'm coercing or asking the malware to decrypt its encrypted strings for me without me having to actually understand how the string encryption works. Work smart, not hard. So as we can see on the slide, I've dumped the majority of the encrypted strings, and we could see the injection technique we used was sufficient, and these strings are very revealing. For example, we can see URL addresses, IP addresses, perhaps of command and control servers. We see an embedded launched item property list. Interestingly, a list of security applications, including Kaspersky, and then perhaps ransom instructions. Again, very insightful. And again, probably giving us insight into the capabilities or the goals of the malware. Finally, during our triage stage, we encounter various anti-analysis logic. We see a function named isVirtualMachine. In the last workshop about Yara rules, there's a question regarding sandbox detection. This is an example of a malware that actually has detection to determine if it's running in a sandbox. And if it is, it'll just exit. There's also other functions, such as one called isDebugging, another one called preventTrace, which seek to prevent the successful debugging of the malware. Right? The malware author has rightfully assumed that if someone is debugging their malware. It's probably a malware analyst like myself trying to uncover the internals of the malware. Luckily, all these anti-analysis logic checks are pretty simple to bypass. We can just set a breakpoint on the function and then skip over them in a debugger. All right, so now we've discussed how to bypass the anti-analysis logic and also decrypted all of the malware's encrypted strings. So full analysis of EvilQuest can commence, starting with analyzing or understanding its persistence mechanism. So we find a function that's named EI persistence main. Seems safe to assume that this is what performs the actual persistence. And if we reverse engineer this function, we can see the malware invoking the anti-analysis logic we just talked about, which we can just step over in a debugger to skip. We also then see it enumerating a list of running processes looking for the popular security tools that, again, were embedded as encrypted strings. Any that are found, the malware will attempt to kill. Probably assumes that these security tools might detect its persistence or some other activity, so it decides just to terminate them. Not the stealthiest, but might be effective. It then invokes a function named persist executable. And via a file monitor, we can observe this function causing the malware to make yet another copy of itself as binary named com.apple.questd. The malware then invokes a method named install daemon, which persists itself both as a launch agent and a launch daemon. The property list for these items, which is a prerequisite for creating either a launch agent or a launch daemon, recall was an encrypted string within the malware. Now, once this function has executed, we can look at the file system and see the plaintext property list file that was created. It's called com.apple.questd.propertylist. It's on the slide as well. And we can see it points to the com.apple.questd binary that the malware just created, which is, again, just a copy of the malware. Now, one thing to note is in this property list, which is a set of key value pairs, there's one that is set to run at load, and this is set to true. And what this does is this tells macOS to please automatically restart the malware anytime the system is subsequently rebooted. So this is how the malware achieves persistence. What the malware finally does at the end of this function is to launch itself for the first time via AppleScript. All right, so now we understand the malware's capability, its persistence. Let's talk about the capabilities. Really, what are the goals of the malware? What's its main, functionality? Now, before we do that, let's briefly discuss how it connects to its command and control server to both check in and request tasking. So if we analyze the malware, we can see it decrypts a hard-coded address of a URL that's hosted on pythonanywhere.com. It then connects to this URL, attempting to read a file named ret.txt, which it expects to contain the actual address of the command and control server. It then connects to that address as specified in that file. Now, if either of these URLs are offline, malware does contain a hard-coded address that it will fall back to for its default command and control server. So one of the first actions taken by the malware, by EvilQuest, is to generate and exfiltrate a recursive directory listing of the infected system. So in a debugger, we can watch this in action. And we can note that the root of this recursive directory listing is /users. Once the malware has completed generating the recursive directory listing, it will send that up to the attacker's command and control server. So now the attacker has a good understanding of at least what directories, what files are on the infected system. The malware will also search for various files that match a list of embedded regular expressions that we can see on the slide. From these regexes, we can see that the malware has, let's say, a propensity for certificates and cryptocurrency keys and wallets. On an infected system, if the malware finds any files that match these, it will collect and exfiltrate them to the attacker. So we can test this, for example, by creating a file named key.png And if we're debugging the malware, we can see that it matches on this file and then scoops it up and exfiltrates it to an attacker. So unfortunately, this means if a user has been infected with this malware, it's likely their private certificates and any cryptocurrency related keying material likely got scooped up and sent to the attacker. EvilQuest also supports a handful of fairly standard commands that afford a remote attacker complete and continuing control over an infected system. So on the slide, we can see the function, the disassembly that implements the logic, including the serialization of a tasking request that gets sent out to command and control server, and then also the deserialization call to deserialize the response, which is the tasking from the command and control server. We then see in the malware's disassembly, it invokes a method, a function named dispatch, which, well, dispatches the commands. And we can see on the slide, there's a table that shows the supported commands that I extracted from the malware. It's all pretty standard stuff, right? Download, execute, kicking off a keylogger, etc., etc. Now, the most interesting of these commands, though, is command number 1, which the malware author has labeled command react exec. And what this function does is it invokes a function named ei run memory _hrd, which executes a encrypted payload downloaded from the command and control server directly from memory. Now, I talked about the specifics of this technique at Black Hat a few years ago, and also noted some example code from Apple that implemented this in-memory code execution. But it's kind of neat to see this ending up in malware as well. And clearly, the benefit of this is that the decrypted payloads never actually hit the file system, right? So this makes them difficult to scan from the point of view of perhaps a file-based AV engine that's only scanning files on disk, or also makes it difficult to collect these payloads for analysis. Because again, they're only decrypted in memory, never actually hit the file system. EvilQuest also supports ransomware logic. This logic is pretty standard in terms of what ransomware normally does. It enumerates all files on the user's file systems that match a predetermined list of extensions, images, documents, etc., etc. And then it invokes a method named carve target for each of these matching target files. What this does is it reads the contents of the file into memory. It then encrypts it into memory, writes out the encrypted contents to a temporary file, deletes the original file, and then renames the temporary file. Kind of a little bit of a roundabout way, but the end result is the original target file is effectively encrypted. Once all the files are encrypted, the malware creates both a README now text document and also displays an alert that contains the ransom instruction. It's kind of funny because it also reads aloud the instructions shown in the alert. If you're analyzing this malware in a virtual machine, once it completes the ransomware logic, all of a sudden your virtual machine will start talking to you, which can be a little bit jarring, especially if you're analyzing this malware, perhaps late at night. Good news is that researchers at SentinelOne figured out that the keying material stored in each encrypted file is actually enough to decrypt the files, so no need to pay. This is interesting, shows maybe the ransomware logic is either incomplete or perhaps a cover for targets that are not of interest. Another observation of this might be that the encryption, the decryption, the ransom instructions don't actually ever provide an email address. So it's kind of like, why is this even in here? And as we'll see in newer versions of the malware, the ransomware logic is actually gone. It was removed. Now, saving the best for the last, EvilQuest is actually a true computer virus. Perhaps the first in the wild computer virus targeting macOS. I'm not aware of any other such computer viruses. Now, by definition, as I'm sure we're all aware, a computer virus replicates itself by modifying other programs, other binaries, and inserting its own code on an infected system, which is exactly what EvilQuest does. As I mentioned, I'm not aware of any other Mac malware that does this, right? Most just, install themselves on the system and go along their merry way. What EvilQuest does, though, is in a background thread, invokes a function called getTargets to get a list of executables on the infected system. And then for each target executable, it invokes a function named append.ei. As its name implies, the append.ei function appends the malware, again, EI stands for effective idiot, into each of these target executables. More specifically, what it does is it inserts itself at the start of the executable while adding a trailer that points to the offset of the executable's original code. The trailer also contains an infection marker. Now, when the infected executable is run, either by the user or by the system, the virus's code will run first. And it performs a variety of logic. For example, it can detect if it's been the other components that have been removed and then reinfect the system. However, to ensure nothing is amiss, the virus then writes out the original code and executes this, right? So if the user double clicks something, for example, a calculator application, they obviously expect the calculator application to run, even if it's been virally infected. The malware ensures that everything appears normal. Now, writing out the original code and executing it is not super stealthy, but it does have a really important benefit, and that is restoring the code signing certificate, the code signing signature of the original file, which must be intact if the original binary contains code signing entitlements, as macOS checks that. So that was somewhat of a whirlwind tour of EvilQuest, aka Effective Idiot. Before we end, I briefly want to discuss some ideas for generic detection, which are actually possible fairly trivially if we focus on behavior-based detections. So first off, it's pretty easy to detect the malware when it persists, as it's persisting an unsigned launch item that's masquerading as an Apple binary. That's shady, right? All Apple binaries are signed. So if you see something that's persisting, that's masquerading as an Apple binary or Apple item, more than likely malware. Nothing else, a big red flag. Also, we can detect the rapid creation of encrypted files by an untrusted process, which makes it pretty easy to detect the malware's ransomware logic, as we've shown on the slide. Finally, if we're monitoring network traffic, say via a firewall, this allows us to detect the malware's unauthorized network communications. Now, the reason behavior-based detections are key or very important is the malware still seems to be evolving. Hence, standard static signature-based approaches may fail. There's been some great research recently published by Trend Micro that kind of covered some of the new updates we're seeing in more recent versions of EvilQuest, which include things like improved anti-analysis logic, the addition of new capabilities, and also, as I mentioned, the removal of the ransomware logic, which always seemed like either perhaps secondary capability or perhaps, as I mentioned, something just to execute on targets that are not of interest, perhaps to cover the more insidious capabilities of the malware. However, I think the coolest update was in the ping command, which now contains the phrase, "Hello, Patrick." Apparently, the malware authors read my initial analysis. Honestly, I've always kind of wanted a shout out in a computer virus, so I was definitely very flattered by this update. Is that wrong? Oh, and one more thing. If you're interested in learning more about Mac malware, Mac exploits, basically the topics we discussed in the talk, I am working on a free book on these topics called The Art of Mac Malware. The first half, and even some subsequent chapters have been published online at taomm.org. And all the rest of the chapters will be published for free online. So the goal is really to create kind of a community resource that contains information about analyzing Mac malware. There wasn't a comprehensive resource for this. So again, if you're interested in analyzing Mac malware, some of the topics we talked about today, hop over to the site and have a read. So I want to end by thanking the organizers of SAS at Home. Definitely super honored to be able to present. I also want to thank all of you for virtually attending my talk. Thanks to my employer, Jamf, who puts up with my shenanigans. And finally, all the companies that support my work at Objective-C. So again, mahalo for attending, stay safe, and hope to see all of you in 2021 in person at the next SAS conference.
Have you seen any leaning towards applications using BP list files for hiding encrypted strings or paths outside of the binary? So far, it seems like it's mostly just Apple stuff that's using BP list.
Correct. Yeah, so BP list or binary property lists are just basically another format that applications or anything can really use to kind of just compress the property lists. Off the top of my head, I really haven't seen a lot of binaries or applications that are not Apple that leverage this. And I'm not sure why. So that might be kind of an interesting heuristics perhaps to detect malware. As the question noted, this also might be a good way for malware to store strings that are not maybe in such a human readable format. So that could have a benefit. For example, if there's signatures that are scanning for ASCII strings, if they've now been stored in a binary property list, the ASCII strings are probably either now compressed or stored in a binary format, so might not be matched. I will caveat though that it's pretty easy to read binary property lists. The APIs actually transparently, if you go to read a property list, will actually convert from binary to XML or plain text for you. So that conversion is done automatically by the APIs. But again, if someone's doing just their own scanning of those property lists, that I agree would be a decent way to store perhaps sensitive information in a way that's not readily readable as a standard property list would be.